just like we're talking about gravimeters as looking at vertical gravity fields, in many cases, the types of magnetometers that we use only measure a vertical field. Sometimes they'll measure a total field, but seldom do we use magnetometers that measure a vector field. Okay, so here is a picture of the inclination, or sorry, the main field total intensity. Okay? So this is the magnetic field across the surface of the Earth. And the largest magnetic field is going to be recorded at the dipoles, typically. And you can see that it gets weaker and weaker, typically, as you go toward the equator. Although, interestingly, the very smallest magnetic field is located offshore South America. And here's the magnetic field inclination. So again, this is the angle with respect to the vertical that a vector magnetic field points. The dipole is right here. That's at 90 degrees. As you go up again toward the north, you see that the dipole increases closer to 90 degrees. Notice where the dipole is 0. Definitely not exactly at the equator. And there's some really kind of funky constant dipoles that go along as you go south. The northern hemisphere is quite a bit more uniform than the southern hemisphere for some reason. And this, as we'll see, has to do with the dynamo in the Earth. Okay, the magnetic field has changed over time. If we look at the dipole, and this is the dipole imaged by declination angle, we can see that the dipole has moved from here in 1831 all the way up to there in 2007. So the dipole changes with time. And this changing dipole is called, we call it a secular variation. It's a secular variation in the dipole, and it's basically caused by convection in the outer core. As most of you probably know, the outer core is what? The inner core is solid iron. What's the outer core? Liquid, right? And we know that because shear waves can't propagate through the outer core. As a liquid, because the Earth is rotating, there's postulated to be a number of things that are going on. There's convection, there's heating and cooling associated with fluids that are going closer to the inner core and then coming back up toward the mantle. So there's a convective conveyor belt, if you will. There's also the Coriolis effect, basically a curl associated with the spinning of the Earth. And those two things create a dynamo, basically a rotating fluid that's primarily oriented, because of the Coriolis effect, along the axis of spin. And that's why the magnetic field is basically the magnetic poles are pretty close to the rotational poles. But they're not perfect, because this dynamo inside is affected by a lot of other things besides the Coriolis effect. And in fact, the dynamo can change directions. And we've seen in the millions of years of history that the dipole polarity of the geomagnetic field has reversed. It flips back and forth many times in the past. So here is actually a picture of the magnetic field simulated. So this is basically just like we were talking about in gravity, right? What we're doing is we're making a model of the fluid in the outer core. We're basically modeling how fluids move there. And from that model, we're creating a magnetic field, okay, an overall magnetic field. So what you see is that it's extremely complex. The magnetic field associated with this fluid movement is extremely complex. Hence, we don't have a nice, neat field intensity at the surface. We don't have a nice, clean vector. It's much dirtier, so to speak, than gravity is. And the cause of this magnetic field, again, is that we have a circulating electric field, right? If we have a circulating electric field, we know that there is a magnetic field associated with the curl of the electric field. And that's from your probably Physics 102 or something like that. So the flow creates the magnetic dipole field. Now, we know that magnetic fields have changed over time. As a matter of fact, we've been able to go back about 780,000 years before the present, and we can look at the particular locations of the dipoles. And the way we're able to do that is with something called remnant magnetization. Anybody know what remnant magnetization is? Well, think about this. If you've got a rock, let's say you've got a basaltic rock in Hawaii, and you have a lava flow, right? Well, when the rock is magma, there's really no magnetic field. It's a fluid, right? But remember, it's got a lot of iron in it, okay? So the magnetic field's all over the place, moving around. What happens when that rock cools? Well, it solidifies, right? It also, once it cools down below what's called the Curie temperature, it solidifies and it embeds a magnetic field associated with whatever the field is at that position into the rock, okay? So you can imagine that, let's say that I'm Hawaii right here, and I get a certain magnetic field embedded into my rock. Okay? So if Hawaii were to move, and obviously it doesn't, it does move up to the northwest here. If I look at that movement over time, I'm going to get a field that's associated not only with however the current magnetic field affects the rock, but how that previous magnetic field affected the rock. So there are two vectors associated with the magnetism in this case, and this is called remnant magnetism. And so what we're able to see in the rock record is the remnant magnetism allows us to look at the movement of these dipoles over time. We're actually able to use those rock records to go way back in time for volcanic rocks and see how the dipole has moved and also when it's flipped. And as we talked about the first day of lecture, that's how they discovered that spreading centers were actually moving rock away. They could actually age date the rock, and they saw the remnant magnetization. So, in general, we've got a dynamo down there, and the magnetic poles are about where the geographic poles are. We define a dipole as a location where the inclination is plus or minus 90 degrees. The magnetic poles are not the same as the geographic poles. They may not even be exactly the same as the geomagnetic pole, which is basically assuming the Earth is a true dipole. The magnetic equator we know is not the same as the rotational equator. And about 10% of the Earth's magnetic field can't be explained by the primary dipole. And as we saw in one of those pictures, the magnitude of the magnetic field, is somewhere between 25,000 to 65,000 nanoteslas. And you can go to Wiki to get a definition of what a nanotesla is. It's a very small magnetic field. Okay? This is a very small number, and I'll show you some examples of what that is. But it's basically, as I recall, it's much, much, much less than the magnet in your refrigerator. So it's a very, very tiny magnetic field that observes. Okay, how do we measure the magnetic field? Well, and we've done this on the moon. We do ground magnetic surveys. This is something called a proton precession magnetometer. Airborne magnetometry has been around for about 50 years. I'm not going to go into the fluxgate magnetometer. That was something that was used very early. It's not used that often today, but it is a vector type of magnetometer. The type that we use in magnetic surveys, and I'm hoping to get one out in the field